Okay, math fans, our topic for today is Note 16-2, solve exponential and logarithmic equations. Our two objectives are, after this lesson, our goal is that you should be able to, 1, solve exponential equations, and 2, solve logarithmic equations by changing them to exponential equations. Before we begin, let me give you your joke of the day. How did Darth Vader know what Luke was going to give him for his birthday? And the answer is, he felt his presence. Presence, yeah. All right, so solving an exponential equation, well, the goal is going to be very simple here. If we can get two expressions that have the same base that are equal to each other, then the exponents will have to be equal. So if this value b raised to the u is equivalent to this value b raised to the exponent v, then we know that u is equal to v. Now we're assuming that the base is positive and not equal to 1. This doesn't work with a negative value for the base. And if the b value was equal to 1, I mean 1 to any power is going to be equal to 1 to any power. I mean, it's going to be equal to 1. Okay, so we assume that these are going to be the situation here. All right, so the concept, very simple. If the bases are equal, then the exponents have to be equal. What we're trying to do is we want to compare the left and the right side in the same way. So for example, number 1, solve the following equations. 2 raised to the x plus 3 is equal to 64. Now the bases are 2 and 64. They are not the same. However, hopefully you recognize that the number 64 can be written in a base of 2. That's actually 2 raised to the 6th power. 2 times 2 times 2 times 2 times 2 times 2 is equal to 64. And so what we're doing here is we are going to rewrite the right side of this equation as 2 raised to the 6th. Now that the bases are the same, we can say that the exponents must be equal. Because this equal sign means that the left side and the right side have the same value. So x plus 3 is 6, and we would subtract 3 from both sides. And there's our answer. We get x is equal to 3. If you want to check that, we can take the calculator and we can go 2 raised to the, we'll take our x value, add 3 to it, and we get 64, the right side, and it's good. Okay, part B, 3 raised to the 2x minus 1 is equal to 1 over 9 to the x. Now, let's first look at the bases here. So this is 3. Now this is 9. They're not the same. However, we can rewrite the number 9 as 3 squared. Okay, now this is 9 raised to the x. Now we need to use some exponent rules here, that when we have an exponent raised to another exponent, what we do is we multiply those. So that's the same as 3 raised to the 2x. Okay, so that's equal to 1 over 3 raised to the 2x power. Now we still have a problem though, because this base is in the denominator. So we're going to use a second rule of exponents, that we're going to take this 3 raised to the 2x and we're going to move this up to the numerator. But when we do that, the exponent that was positive will become negative. So we get 3 raised to the 2x minus 1 is equal to 3 raised to the negative 2x. Now what we're using there is this idea that, for example, x raised to the negative 3 is the same as 1 over x raised to the positive 3. The other rule was if we had x to the 2nd raised to the 3rd, we multiply those exponents and we get x to the 6th power. So we're using our exponent rules to manipulate this. Now that the bases are equal, that means that the exponents have to be equal. So 2x minus 1 equals negative 2x. And now we solve this equation. I would subtract 2x from both sides to get negative 4x, and then divide by negative 4. A negative divided by a negative is positive. So 1/4 is equal to x. Now with any equation, again, we can always check. So if I take the left side, 3 raised to the, that was 2 times 1/4, and then subtract 1. All right, so let's see here. We get a decimal, 0.57735. If we did 1 over, that was 9 raised to the x, and again the x was 1/4, or 0.25, and we get the same thing. Okay, so we know that our answer is good. All right, so we'll do another example here. If you want to, go ahead and pause it, see if you can get this one. One of the things about this is we need to have a good understanding of exponent rules. Okay, so when we look at the number 25, we also need to know some computation. The number 25 can be written in a different base. The number 125 can be written in a different base. Both of these can be written as a base of 5. 25 is 5 squared. Now that is being raised. I can't forget about this exponent, 3x minus 1. 125 is 5 raised to the third power, and that's being raised to the x plus 1 power. Okay, now we have the same base. Let me simplify a little bit in the top here. An exponent raised to another exponent is multiplication. So that would be 5 raised to the 6x minus 2, because we distribute the 2. And this would be 5 raised to the 3x plus 3. Now that we have a common base, that means the exponents themselves have to be equal, so I just write those as an equation. I'll move the 3x to the other side by subtracting it, and at the same time move the minus 2 by adding 2, and we'll get 3x equals 5, divide by 3, x is equal to 5/3, and if we check it, it's good. Okay, always check your answers and make sure that they're working. So now let's look at a couple more examples that may be a little bit more complicated here. Part D, e raised to the negative x squared equals e raised to the x raised to the second power, and then times 1 over e raised to the third power. Now something about this problem is the bases are all e's. So that's actually good. The problem is that we need to have one expression on the left side and one expression on the right side. This here is not simplified. So we want to simplify this to get one expression, e raised to something. Now we can do that. E raised to the x and then raised to the second, we multiply those. So that's e raised to the 2x. We don't want to write this as a fraction. We want the base to be here. Now I'm going to move this up to the numerator, but the rule is when I move an expression, either up or down, the exponent changes. It becomes the opposite of that. So that's e raised to the negative 3. Now, this gives us another situation, a different rule with exponents. When you have the same base and you multiply the expressions, we add the exponents. So if I have x to the second times x to the third, the rule is we add the 2 and the 3 and we get x to the fifth. Okay, so that's what I'm going to do here. Now, we have e to the negative x squared equals, I keep the base, so the base is e, but I add these, but 2x plus negative 3 is the same as 2x minus 3. So now we have a common base. That means that the exponents themselves must be equal, so we make an equation, negative x squared equals 2x minus 3. Now this is a quadratic because we have an exponent that is a 2. I'm going to move that to the other side by adding it, and we get 0 equals x squared plus 2x minus 3. When I have a quadratic, I usually want to have everything on the same side of the equation. All right, now we can factor this. So thinking about this here, the lead coefficient is 1, the constant's negative 3. That's a, b, and c. We want two values that multiply to ac that add up to b. 1 times negative 3 is negative 3. and the middle number, the b value, is positive 2. So what multiplies the negative 3 and adds to 2? That would be positive 3 and negative 1. So we get 0 equals, that's x minus 1 times x plus 3. And then we take each factor, we set those to 0. And we get x is equal to positive 1. And we get x is equal to negative 3. We would go minus 3 minus 3, plus 1 plus 1. Now, it is important that I check these. So I would take your calculator and go ahead and substitute the values. I'm going to tell you that they work. I've already checked them, but it is something that you should also do yourself. Now, part E and part F are a little bit different. Part E, we have 2 raised to the x is equal to 11. Now, this is a problem because 11 cannot be written with a base of 2. I can't set it up where I have 3 raised to something equals 3 raised to something, or 2 raised to something equals 2 raised to something. So what happens when I cannot get a common base? Well, we have another technique here. Just as you can add to both sides, just as you can go plus 2 and plus 2, just as we can subtract on both sides, just as you can divide to both sides of an equation, you can also take the logarithm of both sides of an equation. Now there's a rule, we're going to write this down here on the side. The log base b of m raised to the r, that is actually equal. The problem is that this value, this exponent, this is what we have here. How do I get the exponent or the variable out of the exponent? If I can't get a common base where I can say the exponents are equal, what technique do I have? Well, when you have a logarithm, this exponent, you can actually move it out front, and that's r times the log base b of m. You're allowed to do that. Now there's a proof for that. I'm not going to put the proof here, but that's something that you can ask about in class that we can take a look at. So here's how we're going to use the technique. We're going to take the left and the right side, and because it's an equation, as long as I do the same thing to both sides of the equation, this is a good move. I am going to take the log of both sides. Now I didn't put a base here because I'm trying to keep this as simple as possible. So that's base 10. Okay, remember that if you don't put a number there, that is a base 10. Okay, now if we have the same base, think about this rule with exponents. If the bases are equal, then these exponents are equal. The same thing happens here. Okay, but actually what we'll do here is we'll take the exponent. We're going to use this property. We'll come back to that other rule in a future problem. And this becomes x times the log base 2 equals the log, this is the log base 10 of 2, sorry, equals the log base 10 of 11. Now this is just a number. The log base 2, we can calculate that. That's some decimal value. It's actually in this case, oops, sorry, that was log 10. I want log 2. And that's equal to this decimal here. So what we have here is a variable multiplying some value. To undo the multiplication, we're going to divide by that number. Now the number is not 2. This number is log of 2, log base 10 of 2. So when I divide, I have to divide by the whole expression. That's just 1. And we get x equals the log of 11 divided by the log of 2. Now we're going to calculate that and we're going to get a decimal value. Okay, so we've got log 11, that's our numerator, divided by log 2. And we get 3.459431619, and that's going to keep going and going. Now, I'm going to round it. If you round it to the tenths place, it's okay, but I'm going to go a little further than that. I'm going to say 3.459. I'm going to go to 3 places. So x equals 3.459. The reason I'm going to go that far is I'd like to check this. I'd like to check that 2 raised to my answer, is it equal to 11? Does that actually give me the value on the right side, 11? Okay, now it does not. It gives me 10.99670956. So by rounding it, when I check, I'm not going to get exactly 11, but I should get something very close to it. I do, so this is a good approximation. Just to show you, if I were to use the whole decimal here, the whole answer, if I did 2 raised and tell the calculator to put the whole answer in, there's my 11 right there. Okay, so it's good. And that is the end of part 1.